Welcome to video 10.3 over the colligative properties. Yes, everybody's really excited about this. In this video, we're going to be understanding the concept of colligative properties, and then we're going to learn how to calculate the boiling point elevation and the V freezing point depression. So as we get started, you're going to want your calculator out, and then of course your notes and your pen. So here we go. So a colligative property. Colligative properties are properties that change or are altered when you add solutes or you change the concentration of a solution. So basically, they are properties that we measure or that we see based upon the different concentrations of the solution. So the big example of this is our freezing point depression and our boiling point elevation. Think about what those words mean. Freezing point, depression, boiling point, elevation. Obviously, freezing point depression brings up this concept of lowering a freezing point, and of course, boiling point elevation means we increase a boiling point. So think about this way. Why do we add salt to our pasta when we boil it? Why do we add salt to our sidewalks in the winter? Because when we add impurity to water, it changes the boiling point and the freezing points. When you add salt to boiling water, it actually increases the temperature at which the water boils. So therefore, now your water is at a higher temperature and your food can cook quicker, overall saving you energy. Same thing with salt on the sidewalk. When you add salt to the sidewalk, it will depress, it will lower the freezing point. So therefore, your water, your snow, I should say, will stay as water, will stay as a liquid at a lower temperature opposed to the ice. And so again, this concept, the changing of this depression or elevation, the boiling point or freezing point, depends on the concentration of the solution. So again, these values can be easily calculated with this given equation. So look at this equation. It's a pretty simple, pretty straightforward equation. It tells me the change in temperature equals this constant, this mole constant, times the molality of a solution times what's called the Van Hoff factor. So again, you'll notice that these little b's here is because this is the equation we're going to use specifically for when we're talking about boiling point elevation. If I change those little b's to an F, that's when we're talking about freezing point. So again, this could be a B, it could be an F. The B just refers to boiling point, the F refers to freezing point, but it's really the same thing. Change in temperature equals the constant times the mole concentration times this I number. We've already dealt with change in temperature a lot, not a big deal. We've dealt with constants a lot. This one happens to be a constant value, talking about freezing point and boiling point, depression or elevation. We've talked about mole concentration. Remember, mole is moles of solute over kilograms of solvent. And this I, we haven't talked about Van Hoff factor before, but it's quite simple. It's quite easy. The idea here behind this, the way you calculate this number is you look at the chemical they give you, the solute to be more specific, and you try to decide when that solute is added to water, how many particles will it break down into? How many different species will it break down into? Only our ionic compounds will break down into more than one to give us more than one. Covalent compounds, however, will always give you a Van Hoff factor of 1 because our covalent compounds do not break down in solution. They just remain as their molecule. So to kind of give you some more practice on this, again, this is a really easy concept. You just got to see it and you'll grasp it. But again, it's the number of atoms the compound will break into. So here's some examples. Here is sucrose. This is a covalently bonded compound. It's a molecule, so therefore his Van Hoff would just simply be 1. When you put sodium chloride into water, it will break down into sodium and chlorine. So the one ion compound will break down into 2 particles or the 2 species, the sodium ion and the chlorine. So the fact that this goes from one ion compound into 2 things that when they break up, your Van Hoff number would be a 2 because it's ionic. Here, the Van Hoff number would be 3 because it's ionic and it's going to break down into 1 calcium and give you 2 chlorines. Finally, this number for Van Hoff would be 3 as well because this ionic compound, when it breaks down, is going to give you 1 magnesium and 2 nitrates. Notice my nitrates still stay together as a particle. It still stays together as a single species, but now my off is a 3. So real quick recap, molecules are 1. Ionic compounds break down, just count how many different molecules they have in there, or how many ions they have in there. That's all we're looking at. So let's do a couple practice problems, and that's it. All right, so here we go. What is the freezing point of a solution containing 210 grams of glycerol and 350 grams of water? So as we get started, we need to remember my change in temperature equals the K mol times my I. So like all of our problems, just go through and start labeling things. First of all, my K is given to me. My mol is not given to me, but we know that the mol is, or molality, I should say, is found from moles over kilograms of solute. So again, I'm going to just put solute here just to help you guys remember that. 210 grams, so I need to convert that bad boy into moles. I kind of did this work on my own just to help speed up the video, but you could do that. If you added all those up, you get 92.11 grams. Put in a calculator, you're going to get 2.2798 moles. Remember, do not round until the very end. Keep at least 4, if not 5 decimal places. Now, in order to get my molality, I got to take that number divided by the kilograms of the solvent. The solvent. So essentially, we're going to take that number now, divide it by 0.350 kilograms, correct? Find that number to be 6.51395 mol of glycerol. Now we're going to use our equation. I have my K, I have my M, I need my I. So now look at this equation. What's your I going to be? Based on that chemical formula, what's my I going to be? My I, since this is a covalently kind of compound, would be just a 1. So you can see this is quite simple. I'm just going to see that my change in temperature, since we're talking about freezing point, it is a little f there, of negative 1.86 degrees Celsius per mol times my molality, 6.51395. I like to keep a lot of decimal places there so I don't screw up, times by 1. And of course, when you look at this, I got 3 sig figs, put it in my calculator, and I get negative 12.1 degrees Celsius. Meaning that if I add glycerol to water, the temperature or the point in which it will freeze will drop negative 12 degrees. So remember, that's change in temperature. So let's look at the next problem. Same idea. What is the boiling point? So now when I go to do my change in T, this will have a little B here instead of an F because it's boiling point. What is the boiling point of a solution containing sodium chloride, NaCl, 350 grams of water? They give me my Kb, but again, as we get started, we got to be able to use that constant times the molality times the I. So again, since they give me molality is moles over kilograms, I need to do a little stoichiometry and then do a little division. I also see that I need to find my I. So let's get started. First of all, what's my I going to be? Well, based on this, I know it's going to be an ionic compound based on all we learned this year. It's going to break up into 2 things. So here my I will be 2. Here I'm going to go 210 grams. Divide that by the molar mass of salt, which would be 30, what is that? That is 58.44. 58.44 gives me 3.59343 moles of sodium chloride. Again, I need to turn that into molality. So that gives me moles. Molality divided out, and you should get a concentration of 10.2669 little m. Now we're ready to use our equation. I'm going to go my 0.51 Celsius per mole times that by my concentration, 10.2669 mole, times that by my I, which is 2, and it gave me an answer of 10.4723 degrees Celsius. Now, let me remind you, this all equaled the change in temperature. This asked me, what is the boiling point? So since it's asked me what the boiling point is, I just found the change in temperature. Now you need to remind yourself that water will typically boil at 100 degrees Celsius, correct? So my new temperature now is going to be somewhere along the line of 110.4723 degrees Celsius. I go back, I say I have 3 sig figs, so this answer would be precise to there. So I'm precise to there. So my true and accepted answer would be 110.5 degrees Celsius. Again, hopefully you're seeing that this is all, with a little practice, this becomes very easy to master. Don't forget, I comes from number of species. If it's covalent, if things on the right of the periodic table bond each other, we just put a 1. If it's ionic compounds, we just count how many things are in there. It's how many ions are in there. You could think of that way. There's 2 ions. Last problem, and we're done. A water solution containing an unknown concentration of glucose solution, which I tell you, is found to have a freezing point of negative 0.23 Celsius. What is the mole concentration of that solution? So again, as I get started, we are looking at the idea of change in temperature equals KMI. As I get started, I see that this is a molecule. So my I there would simply just be 1. I see that they give me a freezing point of negative 23. Well, the fact that I know water is typically freezes at 0, and now it went to negative 23, I can see how that is simply my change in T still. So again, just a quick side note there. So I got my change in T, right? And then I need to find my concentration, which they want me to ask. And I can find my K from the slide before. If you go back to your first slide, you will see that your KF is negative 1.86 Celsius per mole. Remember, I'll have to give you that number. That's a constant. I will give you that on all tests and quizzes. A couple of these numbers you might start to memorize a little bit, but again, I'll give you that. All right, so as I can see here, I just went through and labeled things, and that tells me I need to solve for mole. So now I simply rearrange that equation, doing some algebra, and I see that my K and my I are on the bottom to leave my mole on top by itself. Just because we're learning, this would be TF and KF because we're talking about the freezing point. So I'm going to throw those in there to make you feel better about what you're doing. Again, if it was boiling point, that'd be a B&B. Small, subtle labeling issue, not a big deal. So now just plug your numbers in and get your answer. Change in temperature is negative 0.23 Celsius. My I is 1. My KF is negative 1.86 Celsius per a mole, and that mole will go on top, and that is why my final answer would just be 0.12 mole of C6H12O6, because my Celsius cancels out. Because I have 2 sig figs, I'm going to stop at 2 sig figs. Now, only other thing I could do to you guys to make sure you really understand molality is I could have changed this problem and I could have said you had 10 liters, how many moles or how many grams of the water solution. I could have maybe done that, maybe you take this a step further. But really you're going to see that this equation is pretty straightforward. You just got to, again, find your variables, rearrange it, plug and chug. So I hope you are seeing that this is not too bad. Long story short, we have colligative properties that change based on the concentration of the solution, and that our freezing point and boiling point elevations are considered colligative properties, and we can calculate those. have a wonderful rest of your day.